Every night, billions of stars look down at you in silence. Scientists have confirmed there are more planets in this galaxy alone than grains of sand on every beach on Earth. The math says the universe should be overflowing with intelligent life, and yet nothing. No signal, no visitor, no trace, just silence so deep it borders on impossible. Tonight, we cut through every serious theory scientists have proposed to explain that silence. From a galaxy-wide extinction machine to civilizations hiding in terror to the staggering possibility that we are the very first minds to ever ask this question. If this keeps you up at night, like and subscribe. Now, prepare yourselves. We begin. The universe is approximately 13.8 billion years old. In that enormous stretch of time, stars formed, planets cooled, and the raw ingredients for life scattered across hundreds of billions of galaxies. The math is not complicated. It overwhelmingly suggests that life should have emerged countless times in countless places long before humans ever existed. And yet every telescope we point at the sky returns the same answer. Silence. This is the Fermi Paradox, named after physicist Enrico Fermi, who in 1950 asked a question so simple it still rattles scientists today. If the universe is this old and this large, and the chemistry of life appears this readily, then where is everybody? Here is what makes the question genuinely unsettling. We are not just talking about a missing radio signal from a distant planet. We are talking about the complete total absence of any detectable evidence of intelligence anywhere outside Earth. No artifact, no megastructure, no engineered signal. A universe this vast, this old, and this chemically rich should be overflowing. Instead, it looks empty. To understand the weight of that silence, consider scale for a moment. Our galaxy alone contains somewhere between 200 billion and 400 billion stars. Astronomers have confirmed that most of those stars host planets. Significant fraction sit in what scientists call the habitable zone, where liquid water can exist on a surface. If even 1 in a million of those planets developed intelligent life, our galaxy alone would host hundreds of thousands of civilizations, many of them millions of years older than us. A civilization just 1 million years more advanced than humanity would have had time to explore every corner of this galaxy, many times over, even using technology only slightly beyond our own. The question is not just where are the aliens? The deeper question is, why has nothing reached us? No probe, no transmission, no engineered artifact drifting through our solar system. That absence requires an explanation. Scientists have proposed dozens over the decades. Some are reassuring, most are not. They range from the possibility that life is far rarer than we assume to the terrifying idea that something systematically prevents civilizations from surviving long enough to make contact. Each explanation carries its own implications for what our future might look like. Before we explore those theories, it is worth sitting with the strangeness of the problem itself. Every time humanity has searched for signals, we have used radio telescopes scanning specific frequencies, optical telescopes hunting for laser pulses, and automated surveys cataloging unusual stellar behavior. The searches have been limited, yes, but the silence has been consistent. Some researchers argue our search is too narrow, that we are listening for one type of signal in a universe that might communicate in ways we have not yet imagined. That is a fair critique, and it makes the problem harder, not easier to dismiss. What Fermi understood in 1950 and what keeps researchers awake today is that the silence is not just curious, it is almost mathematically suspicious. The universe had every opportunity to fill itself with minds. Something stopped it. What that something is, and whether it is behind us or still ahead, is the question that changes everything. Because the next theory we are about to explore does not just describe the silence. It suggests the silence may be the most important warning humanity has ever received. In 1960, astronomer Frank Drake stood at a chalkboard and wrote an equation that was never meant to give answers. It was meant to organize ignorance. The Drake equation laid out every variable required to estimate the number of communicating civilizations in our galaxy right now. And when you work through it honestly, it does something unexpected. It reveals exactly where our certainty ends and where the terror begins. The equation multiplies several factors together. How many stars form in our galaxy each year? How many host planets? How many planets sit in the habitable zone? Of those, how many develop life? Of those, how many develop intelligent life? How many build a technology capable of communication? And finally, for how long does that civilization survive and broadcast? The first few variables are now well understood. Astronomers have confirmed through decades of observation that our galaxy produces roughly 1 to 3 new stars per year. Most host planetary systems. A substantial fraction include planets at the right distance for liquid water. These numbers, confirmed by the Kepler Space Telescope and follow-up missions, suggest hundreds of millions of potentially habitable worlds in our galaxy alone. Then the equation hits a wall. The moment you reach the question of how many habitable planets actually produce life, scientific certainty evaporates. We have exactly one confirmed example of life in the universe: Earth. Every estimate beyond that is extrapolation. Some astrobiologists believe life emerges almost inevitably wherever conditions allow because the chemistry is so robust. Others argue that even on Earth, the leap from chemistry to a living cell may have been a near miracle that took hundreds of millions of years and enormous luck. That single unknown swings the final answer from millions of civilizations down to one: us. And we have no way yet to know which estimate is closer to reality. But here is where it gets stranger. Even if we assume life emerges relatively easily, there is another term in the equation that quietly swallows everything. The last variable, the lifespan of a communicating civilization. How long does any technologically capable species survive before it goes silent? If civilizations typically last only a few thousand years after reaching radio capability, which is roughly where humanity sits right now, the galaxy could be full of brief candles blinking on and off, never overlapping in time. Two civilizations might each exist for 1,000 years, but be separated by millions of years. They would never meet. They would never hear each other. This possibility is known as the temporal spacing problem, and it is one of the more quietly disturbing solutions to the Fermi Paradox. Not a dramatic extinction event, not a cosmic predator. Just time, vast and indifferent, keeping every mind in the universe apart. Drake himself ran the equation at a conference in 1960 and estimated there might be 10 communicating civilizations in our galaxy. Modern estimates range from less than 1 to tens of millions, depending entirely on how optimistically you fill in the unknowns. That range tells you everything. We are not close to solving this. We are standing at the edge of the unknown. And one of the darkest explanations for why that equation keeps returning low numbers involves something scientists call the Great Filter. The Great Filter is not a place. It is not a thing you can point to in space. It is a concept first formalized by economist Robin Hanson in 1998, and it may be the most disturbing idea ever put into clean, logical words. The premise is simple. If intelligent life is possible, and the universe is old enough to have produced it countless times, but the galaxy appears empty, then something must be filtering civilizations out before they become widespread. Something is stopping life from reaching the stars. The filter could be a single catastrophic barrier or a series of smaller ones. It might operate at the level of chemistry, preventing life from starting. It might operate at the level of biology, preventing complex cells from forming. It might operate at the level of intelligence, preventing animals from developing technology. Or it might operate at the level of civilization itself, preventing any species from surviving long enough to become interstellar. The terrifying part is not the filter's existence. It is the question of where it sits relative to us. If the great filter is behind humanity, we are extraordinarily lucky. We already survived the hardest step, the emergence of life, the evolution of complex cells, the development of intelligence. One of these transitions was so improbable that almost no other species in the galaxy made it through. We did, and if that is true, the road ahead may be open. We may be one of the very few minds in this galaxy, perhaps the only one with a real future among the stars. But if the great filter is ahead of us, the implications reverse entirely. Every civilization that reaches our level of development eventually hits a wall it cannot survive. Nuclear war, environmental collapse, artificial intelligence that escapes control, some technology not yet imagined, turning against the species that created it. In this scenario, the silence of the universe is not a mystery. It is a warning. Every civilization before us tried to cross this threshold and failed. We are approaching it now. There is a way to estimate which scenario is more likely, and the method will unsettle you. Finding life elsewhere would normally feel like a triumph, but under the logic of the great filter, it would be cause for alarm. If we discover microbial life on Mars or complex organisms in the oceans of a distant moon or signatures in the atmosphere of an exoplanet, it means the emergence of life is not the filter. Life is common, which means the filter must lie further along the path. Closer to us, possibly ahead. The more life we find in the universe, the worse our odds may become. This is confirmed scientific framing. Though the filter itself remains theoretical, no physical law prevents civilizations from spreading. The absence of evidence for any spreading civilization is real, documented, and unexplained. What we do know is this: the silence is real. The math demands an explanation, and whatever is doing the filtering, it is effective enough to have emptied a galaxy. The next question is whether that filter is a product of the universe itself or something far older and more deliberate. The question of whether the great filter is behind or ahead of humanity is one of the most consequential in all of science. Two researchers can look at the same data and reach completely opposite conclusions. Both reasonable, one ending in hope and the other ending in something close to dread. The case for the filter being behind us rests on a series of biological milestones that each look in hindsight absurdly improbable. The first is the origin of life itself. For hundreds of millions of years after Earth formed, it was a lifeless rock. Life did not emerge instantly from available chemistry. It took enormous time and, by most estimates, a staggering run of molecular luck. The exact mechanism by which the first self-replicating molecule appeared is still not fully understood. This is confirmed. Scientists do not have a complete model for abiogenesis, the process by which chemistry becomes biology. But that may not even be the hardest step. About 2 billion years after simple bacteria appeared, something stranger occurred. One bacterium was absorbed by another cell, and instead of being digested became a permanent internal structure. That partnership produced the mitochondria. That event produced the complex cell, the foundation of all multicellular life. It appears to have happened exactly once in 4 billion years of Earth history. Every plant, animal, and fungus alive today descends from that single improbable merger. If events like these are the filter, then we survived them, and the road ahead has at least the possibility of being navigated. The case for the filter being ahead is harder to dismiss and, honestly, harder to sit with. Consider the behavioral pattern of every civilization we can observe. Our own. Humanity reached radio capability roughly 100 years ago. In that same century, we developed nuclear weapons capable of ending civilization, began altering the atmosphere in ways that threaten global stability, and started building artificial intelligence systems whose long-term trajectory no one can fully predict. We are, in the language of risk assessment, a species that gains catastrophic power faster than it gains the wisdom to manage it. If this pattern is universal, if every species that reaches technological capability does so before it reaches sufficient maturity to handle the consequences, then the filter ahead is not a cosmic accident. It is a developmental trap, a phase every species enters and most do not leave. There is a third possibility that few researchers discuss openly. The filter may not be a single event. It may be a series of compounding barriers, each one reducing the population of surviving civilizations until the number that reaches interstellar scale rounds to zero. Under this model, no single step kills everyone. But each step thins the herd enough that by the time a civilization could be detected, statistically none remain. This remains theoretical, but it fits the data we have. We are standing at a specific point on this path. We have survived the early barriers at least partially. Whether the hardest ones are already behind us, or whether we are approaching the edge of the most dangerous threshold any civilization ever faces, we genuinely do not know. What we do know is that the next theory offers a very different explanation, one that requires no destruction at all. In 1998, paleontologist Peter Ward and astronomer Donald Brownlee proposed something that cut against decades of optimistic thinking about life in the universe. Their argument was not that life is impossible elsewhere. It was that complex, multicellular intelligent life requires such a precise combination of conditions that Earth may be genuinely extraordinary. Not just lucky, extraordinarily, almost impossibly lucky. The hypothesis begins with location. Earth does not sit just anywhere in the galaxy. It orbits in what astronomers call the galactic habitable zone, far enough from the dense, radiation-saturated galactic center, but not so far out that heavy elements needed for rocky planets become scarce. Stars in the inner galaxy are bombarded by gamma-ray bursts and supernova shock waves far more frequently. Stars in the outer regions lack the chemical richness to build complex worlds. Earth sits in a narrow band where conditions remain survivable over billions of years. That is just the beginning. Our star is a quiet, stable, middle-aged star that has not dramatically changed its energy output in billions of years, giving lifetime to evolve. Many stars are more variable, more violent, or too short-lived for complex evolution to occur. The position of Earth within this system is also unusual. We have a large companion in our moon whose gravitational influence stabilizes Earth's axial tilt. Without that stabilization, our planet's axis would wobble chaotically, causing extreme climate swings that would likely prevent the development of stable ecosystems. Then there is Jupiter. The largest planet in our system acts as a gravitational shield, absorbing or deflecting a significant fraction of the comets and asteroids that would otherwise strike Earth at a far higher frequency. More impacts mean more mass extinction events. More extinctions mean less time for complex life to stabilize and develop. Jupiter's presence may have been essential. Add plate tectonics that recycle carbon and regulate temperature over millions of years. A magnetic field that deflects lethal radiation. An oxygen atmosphere produced by early photosynthetic life. And the narrow temperature range that kept liquid water stable across billions of years. And what emerges is not a picture of a typical planet. It is one of an extraordinarily fine-tuned system where dozens of factors aligned in sequence. Ward and Brownlee argued that while simple microbial life might be common in the universe, the full stack of conditions required for complex life is so rare that Earth-like planets capable of producing intelligence might number in the dozens per galaxy or fewer. This hypothesis remains debated. Some astrobiologists push back strongly, arguing that life is adaptable enough to work around many of these constraints. But the rare Earth argument remains one of the most scientifically grounded responses to the Fermi Paradox. It does not require a filter or a catastrophe. It requires only that complexity is genuinely hard to produce. If Ward and Brownlee are right, the silence has a quiet explanation. Not that civilizations rise and fall, but that the conditions for intelligence were almost never met in the first place. It is a strangely lonely answer, but it may not be the strangest one on our list because the next hypothesis does not suggest that other civilizations failed to form. It suggests they formed, thrived, and made a deliberate decision about us. In 1973, astronomer John B. proposed something that sounds almost comforting until you think about it long enough. His idea, known as the zoo hypothesis, suggests that intelligent civilizations do exist in the galaxy, advanced ones, possibly ancient ones, and they know we are here. They simply choose not to make contact. The reason, B argued, could resemble what we do with wildlife preserves or isolated communities. We observe, we study, we do not interfere. Not because we are indifferent, but because we understand that uncontrolled contact destroys the thing you are trying to observe. If a civilization millions of years older than us decided to monitor Earth, they would have excellent reasons to stay invisible. Think about what happens when a technologically superior culture makes contact with a less developed one. History gives us a consistent answer. The less developed culture is overwhelmed. Its social structures collapse. Its belief systems fracture. Its sense of identity disintegrates. An alien civilization wise enough to have survived millions of years would almost certainly understand this dynamic better than we do. Non-inference may not be cruelty. It may be the most ethical possible response to finding a young, fragile civilization. Under this hypothesis, the silence is not empty. It is managed. There could be an entire network of older civilizations that have agreed formally or through long cultural tradition to leave developing species alone until some threshold is crossed. That threshold might be a certain level of technological capability. It might be a demonstrated capacity for cooperation at a global scale. It might be something we have not yet achieved and cannot define from our current position. The zoo hypothesis is by its nature extremely difficult to test. If a civilization is advanced enough to hide from our instruments, we would have no way to detect it. Every anomaly we dismiss as natural could in principle be managed. The hypothesis survives precisely because it cannot be ruled out. But it raises an uncomfortable follow-up question. If we are in a zoo, what happens when the exhibit changes? In the last century, humanity has gone from horse-drawn carriages to nuclear weapons to artificial intelligence to the edge of interstellar communication. If there is a threshold for contact, we may be approaching it, faster than anything in our previous history would suggest. And the question of who decides when we are ready and what contact actually looks like when it arrives is one we have no framework for. Some researchers extend the zoo hypothesis into something slightly darker. Not a preserve maintained out of kindness, but a quarantine maintained out of caution. A civilization that has watched other young species destabilize their regions of space might isolate emerging civilizations, not for the newcomer's benefit, but for the safety of everyone else. In that version, the silence is not a gift. It is a fence. This remains theoretical. There is no confirmed evidence of alien observation or management of Earth. But absence of evidence is not evidence of absence, particularly when the entity doing the hiding may be millions of years ahead of us in every field. What we do know is that the zoo hypothesis, however unsettling, assumes something almost reassuring that advanced civilizations survive long enough to become wise. The next theory assumes something entirely different. It assumes that in a galaxy full of intelligent life, wisdom is a luxury none of them could afford. The dark forest theory comes from a thought experiment so bleak it is difficult to sit with. Popularized by Chinese science fiction author Liu Cixin. The underlying logic is not fiction. It is a game, theoretic argument about survival in a universe where resources are finite and intentions cannot be verified. The argument begins with two axioms. First, every civilization's primary drive is survival. Second, the universe does not contain enough resources for unlimited expansion by unlimited civilizations. From these two premises alone, the theory draws a devastating conclusion. Imagine you are a civilization that has just detected a signal from another intelligent species. You know nothing about them except that they exist and can broadcast. Now you face a choice. You could attempt contact and hope for cooperation, but you cannot verify their intentions. You cannot know if they are peaceful or predatory. If they are peaceful and you make contact, you gain a potential ally. If they are predatory and you make contact, you reveal your location to something that may want to eliminate you. If they are peaceful and you destroy them preemptively, you lose one ally. But if they are predatory and you destroy them preemptively, you survive. The mathematics of this situation, under assumptions about resource scarcity and the impossibility of verifying intent across interstellar distances, push toward one rational conclusion. Strike first always. Under the dark forest model, the galaxy is not quiet because life is rare or because civilizations are fragile. It is quiet because every civilization that survives long enough to understand the stakes goes silent. Broadcasting your presence is not an invitation. It is a death sentence. Every star is a potential hunter. Every civilization, a creature, moving through the dark, making no sound, leaving no trace, hoping nothing notices it. the implications for our own behavior are disturbing. Humanity has been broadcasting radio waves for over a century. Those signals have already traveled more than 100 light-years into space, reaching thousands of stellar systems. If the dark forest model is correct, we have already made the worst possible mistake. More alarming still, certain researchers have proposed that we should stop broadcasting immediately. The debate about whether humanity should actively send powerful targeted messages toward distant stars has become genuinely contentious among scientists precisely because of arguments like this one. Stephen Hawking, before his death, publicly warned against it. The dark forest theory is not confirmed science. It is a theoretical framework built on logical premises. Its weakest point is the assumption that cooperation is never worth the risk. Some researchers argue that civilizations advanced enough to be dangerous would also be advanced enough to recognize that mutual cooperation offers greater returns than mutual destruction. But that argument assumes rationality scales with technology. History offers limited support for that assumption. There is also a quieter version of this idea that requires no malice at all. Simply the recognition that contact between civilizations of vastly different capability levels is inherently destabilizing, and that advanced species may go silent not out of aggression, but out of informed caution. Either way, the universe goes dark. And if you think the dark forest is the most unsettling explanation on this list, what comes next makes it look almost peaceful. Every civilization in human history has eventually ended. Empires, cultures, city-states, languages, species. The pattern of rise, flourishing, and collapse is so consistent in the natural and human record that it barely registers as remarkable anymore. But when you apply that pattern to the Fermi Paradox, it stops being background noise and becomes the loudest possible signal. The self-destruction hypothesis holds that intelligent civilizations routinely eliminate themselves before they can make meaningful contact with others. Not through cosmic accidents, not through alien predators, through their own creations and their own decisions. The timing is what makes this hypothesis so hard to dismiss. In the roughly 250,000 years that anatomically modern humans have existed, we spent nearly all of it as small scattered bands with negligible impact on the planet. Then, in the last 12,000 years, we developed agriculture, cities, and organized societies. In the last few hundred years, we built industry. In the last 100 years, we split the atom, altered the climate, and began constructing systems of artificial intelligence that no single person fully understands or controls. The acceleration is the problem. Every century that passes, humanity's capacity for accidental or intentional catastrophe expands faster than our ability to govern it. Nuclear arsenals exist today, capable of ending complex life on Earth. Engineered pathogens are becoming increasingly accessible as biotechnology advances. Climate disruption is already reshaping the conditions that support current civilization. And artificial intelligence is developing along trajectories that even its creators describe as potentially ungovernable. These are not science fiction scenarios. They are confirmed, documented technological realities. The self-destruction hypothesis asks a simple question. If this pattern of accelerating power combined with lagging wisdom is universal among intelligent species, how many civilizations survive the transition from planetary to interstellar capability? If the answer is close to zero, the galaxy fills with brief, brilliant civilizations that torch themselves before sending a single probe beyond their home system. There is a specific window that researchers sometimes call the critical phase. It is the period between a civilization gaining planetary scale destructive power and gaining either the wisdom to manage it or the technology to escape the planet entirely. On Earth, that window opened roughly in the middle of the 20th century and shows no sign of closing. How long it stays open before something catastrophic happens through it is a question no one can answer with confidence. What makes this especially relevant to Fermi is scale. Even if 99 out of every 100 civilizations survive their critical phase, the galaxy would still host thousands of survivors. The silence would remain inexplicable. For this hypothesis to fully account for the emptiness, the survival rate would need to be extraordinarily low, possibly close to zero. And that when you sit with it, honestly says something about us right now in this century. We are not observing a past civilization that failed. We are living inside the critical phase. We are the experiment, whose outcome is not yet determined. Some researchers believe the fact that we are still here, still talking, still searching the sky is evidence that something in our nature bends towards survival. Others are less optimistic. What comes next does not wait for civilizations to destroy themselves. It proposes something in the galaxy takes a far more active approach. The berserker hypothesis is not a metaphor. It is a specific logical proposition about what a sufficiently advanced civilization might do to secure its long-term survival. And once you understand the reasoning, it is very difficult to stop thinking about. The concept was introduced in science fiction by Fred Saberhagen. But the underlying logic has been taken seriously by researchers in astrobiology and existential risk. The hypothesis proposes that at some point in the galaxy's history, one or more civilizations built self-replicating autonomous probes with a single instruction: destroy any other civilization you find before it can become a threat. To understand why a civilization might do this, you have to think in long time scales. A civilization that survives tens of millions of years eventually faces a problem. Other civilizations, if allowed to develop, will eventually reach comparable capability. At that point, the older civilization's dominance is no longer guaranteed. From a purely strategic standpoint, the rational move is to eliminate competitors early before they become dangerous. Rather than waiting for a confrontation at equal strength, self-replicating probes solve the problem of scale. You do not need a fleet of ships to patrol the galaxy. You build one probe that can mine raw materials from asteroids, construct copies of itself, and disperse. Over millions of years, a single original probe becomes trillions, spreading through the galaxy like a slow, methodical tide. Any planet showing signs of technological development gets flagged, then eliminated. Under this model, the silence of the universe has a simple explanation. We have not been found yet. Or maybe we have, and the countdown has already started. That second possibility is not comfortable to sit with. There is no confirmed evidence of berserker probes, no detected artifacts, no observed destruction events that cleanly fit the profile. But here is the difficulty. If the probes are designed to be stealthy, we might not recognize them. If they are patient, they might wait until a civilization crosses some specific threshold of development before acting. We would have no warning. Some researchers have noted that Oumuamua, the mysterious interstellar object that passed through our solar system in 2017, could theoretically fit the profile of a probe. This is not the scientific consensus, which leans toward natural explanations, but the object behaved in ways that did not fully match any known natural model, and the question remained open longer than most anomalies do. The Berserker hypothesis also offers a grim framing for a pattern in the astronomical record. Several of the most promising nearby star systems for hosting life-bearing planets appear to have experienced significant disruption events in their past. The causes remain debated. What gives the Berserker concept its staying power is not any single piece of evidence. It is the logical consistency of the premise. In a universe where survival competition is real and technological capability grows without limit, preemptive elimination is a coherent, long-term strategy. It is horrifying precisely because it makes sense. The galaxy may not be silent because life is rare or fragile. It may be silent because something already swept through and made it that way. And if that is even partially true, the most important question facing humanity is not how to find other civilizations. It is whether finding them would be the last thing we ever do. But here is what no one expects. The next theory involves no destruction at all. It involves speed, and it rewrites the entire timeline. In 2020, a team of astrophysicists, including Robin Hansen, proposed a model that reframes the Fermi Paradox in a way that cuts through most of the speculation. Their framework, which they called the Grabby Aliens model, starts from a single assumption. When civilizations reach a certain level of technological capability, they expand fast and permanently. The model does not assume hostility. It does not require self-replication or destruction. It simply assumes that a technologically advanced civilization, given sufficient time, will spread outward through space at a significant fraction of light speed, colonizing star systems and leaving behind a visible expanding boundary of altered space. The key insight is what this implies for timing. If such civilizations existed and started expanding even 1 billion years ago, their expanding boundaries would already have reached us. The galaxy is old enough, and the physics of expansion at even a modest fraction of light speed is fast enough that any civilization with a significant head start would have made contact by now. Not through a radio signal, but by physically arriving. The fact that we have not been absorbed, contacted, or even brushed by the expanding edge of any such civilization is itself significant data. Under the Grabby Aliens model, this means one of two things. Either there are no such civilizations because something prevents them from reaching the expansion phase, or they exist but have not started yet. Meaning we are very close in cosmic time to when the first Grabby civilizations will emerge, and we might be one of them. This second possibility carries a striking implication. If Grabby civilizations are rare but inevitable, and if we are close in cosmic time to when the first ones appear, then humanity may be among the very first species to reach this threshold. We are not late to the party. We are early, extremely early. The model predicts that if you looked at the universe in 1 billion years, assuming humanity or its descendants have expanded, you might see the cosmos filling with competing spheres of influence from multiple originating civilizations, each growing outward at fractions of light speed, eventually meeting at boundaries and establishing some form of equilibrium or conflict. Right now, the universe looks empty because the expansion age has not started yet. The window of silence we observe may be temporary, a cosmic morning before a very loud day. The Grabby Aliens model has been peer-reviewed and taken seriously in academic circles. It does not resolve every edge of the Fermi Paradox, but it offers a mathematically coherent answer to the timing question. We see no expanding civilizations because the expansion age is only just beginning. Whether this is reassuring or alarming depends on your perspective. On one hand, we may simply be first, not alone in a dangerous universe. On the other hand, if we are among the first grabby civilizations to emerge, then the choices we make in this century about how we expand, what we consume, and how we treat the life we encounter will set a precedent that echoes across billions of years of cosmic history. That is not a small responsibility. But not everyone thinks the answer to the Fermi Paradox is written in the stars. Some think it might be written in the code of reality itself. And the next theory is arguably the strangest one yet. The simulation argument was formalized by philosopher Nick Bostenram in 2003, and it is worth understanding on its own terms before connecting it to the Fermi Paradox. Bostenram's argument does not claim we are in a simulation. It presents a trilemma. One of three things must be true. Either almost all civilizations at our level of development go extinct before becoming capable of running detailed simulations of conscious minds, or almost all technologically mature civilizations choose not to run such simulations. Or we are almost certainly living inside a simulation right now. The logic is straightforward. If even one civilization in the history of the universe survived long enough and chose to run detailed simulations of minds, it could run an astronomically large number of them. The simulated minds would vastly outnumber the real ones. Therefore, any randomly selected mind, including yours, is statistically far more likely to be simulated than real. Now, connect this to Fermi. If we are inside a simulation, the silence of the universe has a trivial explanation. The sky is empty because the programmer did not populate it. No other civilizations are broadcasting because no other civilizations were rendered with sufficient detail to broadcast. The universe exists only as far as its observers require. Beyond the edge of our instruments, there may simply be nothing, not empty space, the absence of code. This is not a scientific hypothesis in the traditional sense. It cannot currently be tested, but it is not pure philosophy either. Several physicists have proposed theoretical experiments that might detect signatures of discretized spacetime, the kind of artifact you would expect if physical reality were built on a computational grid rather than continuous mathematics. Those experiments have not returned a definitive result. The question remains genuinely open. From a Fermi perspective, the simulation solution is both the cleanest and the most structurally strange. It requires no great filter, no self-destruction, no alien hunters. It requires only that we accept the possibility of a layer of reality above the one we can observe, and that whoever operates that layer chose not to include other voices in our rendering of the cosmos. Some physicists push back by pointing out that simulating a universe with the physical detail we observe would require computational resources that may be impossible even for an arbitrarily advanced civilization. This is a fair objection, but it is not a definitive refutation. We do not know the computational limits of an entity operating outside the constraints of our physics. What makes this theory compelling in the context of Fermi is its explanatory simplicity. The silence is not a puzzle to solve. It is a design choice. And if it is a design choice, the question shifts entirely. Not where is everybody, but why were we made to feel alone? That question has no scientific answer yet, but it has a quality that distinguishes it from most Fermi solutions. It makes the silence feel intentional, curated, purposeful. Whether that possibility is comforting or deeply disturbing likely says more about the person hearing it than about the universe itself. What we visit next is not philosophy, it is hard biology. And it may be the most grounded, most sobering explanation on this entire list. For most of the 20th century, the dominant assumption in astrobiology was that life, once it starts, tends to get more complex over time. Simple organisms become multicellular. Multicellular organisms develop nervous systems. Nervous systems develop brains. The story seemed to have a natural escalator, and Earth was just one of billions of planets riding it. That assumption has been quietly dismantled over the past 2 decades. Not through a single dramatic discovery, but through the accumulation of detail about just how contingent and fragile the path from simple to complex actually was on Earth. Consider the timeline. Life appeared on Earth within a few 100 million years of the planet's formation. That is relatively fast, geologically speaking, and suggests that the origin of simple life may not be the main barrier. Single-celled organisms dominated Earth for roughly 3 billion years. 3 billion years of chemistry, of evolution, of environmental pressure and life went nowhere structurally complex. Then the eukaryotic cell appeared. This is the cell type that forms the basis of every complex organism alive today. Every plant, animal, and fungus. As explored. Earlier, this cell arose from a single symbiotic merger between 2 different organisms. One cell absorbed another, and instead of digesting it, retained it as an internal energy-producing structure. This produced the mitochondria. Scientists believe this event happened exactly once in 4 billion years of Earth history. Once in 4 billion years with no evidence it has happened anywhere else. After the eukaryota appeared, another billion years passed before multicellular life became widespread. Then came the Cambrian explosion, the geologically sudden appearance of most major animal body plants, which may have been triggered by atmospheric oxygen reaching a critical threshold, not a gradual progression, a threshold event. Each of these transitions required a specific precondition. The chemistry had to be right. The environment had to be stable for long enough. The random mutation required had to occur at exactly the right moment in exactly the right organism. Miss any one of these and the escalator stops. You get a planet of bacteria indefinitely. Researcher Andrew Null of Harvard has spent decades studying early Earth life and argues consistently that the emergence of complexity was neither inevitable nor predictable. It was a series of accidents stacked on accidents, each one necessary for the next. From a scientific standpoint, this is not pessimism. It is an honest reading of the fossil and molecular record. If this analysis is correct, then the universe is probably not empty of life. It is probably full of bacteria, simple organisms thriving in OCE beneath ice shells and in warm subsurface rock formations across thousands of worlds. But the leap to complexity, to nervous systems, to brains, to language and technology may have happened only a handful of times in the entire observable universe. Simple life, likely common, confirmed possible on at least one world. Complex life, possibly the rarest thing in existence. The silence of the sky is not because the universe is dead. It is because complexity is a nearly impossible accident that happened to us and almost nowhere else. And if that is true, the stakes of our survival just increased by several orders of magnitude. Because what we explore next is the possibility that not only is complex life rare, but that intelligent technological life may have happened exactly once here us. There is a version of the Fermi solution that requires no catastrophe, No filter, no alien hunters, and no simulation. It requires only a specific reading of probability combined with the known age and structure of the universe. And its conclusion is this: we may be the first intelligent civilization to ever exist anywhere. The idea does not rest on arrogance. It rests on timing. The universe is 13.8 billion years old. For roughly the first 9 billion of those years, the conditions for complex rocky planets like Earth were not well established. The first generation of stars contained almost no heavy elements. They burned bright and died fast, seeding the universe with carbon, oxygen, iron, and the other atoms required for chemistry and biology. Only after multiple generations of stellar birth and death did enough of those elements accumulate to build the kind of world Earth represents. Our planet formed about 4 billion years ago. Complex life took over 3 billion years to emerge. Technological intelligence took another several 100 million years. On top of that, when you place humanity on the timeline of cosmic chemical enrichment, we appear at almost the earliest possible moment that beings like us could exist, not billions of years late to a crowded party, right at the beginning. If the emergence of intelligence requires the heavy element richness that only became widespread roughly 5 to 8 billion years ago, and if intelligence also requires several billion years of biological evolution to develop, then there is a narrow window at the front edge of possibility where the first minds could emerge. We may be sitting in that window right now. Under this framing, the universe is not old enough to be full of intelligence yet. We are not survivors of a galactic purge. We are not undiscovered by a wiser civilization. We are simply early, the first species or one of the very first in a universe only just reaching the point where such crossings are possible. The implications are staggering. If we are first, everything that happens next is a blank page. There is no elder civilization to learn from, no template to follow, no warning from a predecessor who already made the catastrophic mistakes. We make the first footprints in what may eventually become a cosmos full of intelligence, but only if we survive to pass something forward. This is not a confirmed conclusion. It is a theoretical possibility consistent with current cosmological data. Researchers like David Kipping at Columbia University have published work suggesting that the distribution of intelligence emergence times across the universe may genuinely favor very early emergence for the first civilization, placing us at or near that leading edge. The loneliness of this hypothesis is different from other Fermi solutions. It is not the loneliness of the last survivor. It is the loneliness of the first arrival, a universe full of potential, none of it yet realized, and us standing at the beginning of something that has never happened before. There is a weight to that. If we are first, the survival of Earth's civilization is not just our concern. It is the only thread connecting the universe to the possibility of a future full of minds. And if that is not enough to sit with, the next chapter will introduce something that suggests our search strategy itself may be the entire problem. The search for extraterrestrial intelligence has been dominated for decades by one method: radio telescopes pointed at specific frequencies, listening for structured signals that natural processes would not produce. This approach began formally in 1960 with Project Ozma and has continued through various programs since. It is reasonable, it is scientifically sound, and it may be completely missing the point. Here is the problem. Radio waves spread out as they travel. The energy disperses across an ever-growing sphere of space. By the time a signal has traveled a few hundred light-years, It is diluted to a level that is extraordinarily difficult to distinguish from the background noise of the universe. Our own most powerful intentional broadcasts, the Arecibo message sent in 1974, would be essentially undetectable to current human technology at even a fraction of the distance to the nearest stars. This means that even if hundreds of civilizations were broadcasting with technology equivalent to ours, we would almost certainly not detect them from interstellar distances. Radio is not a good interstellar communication medium for civilizations at our level of development, and civilizations significantly more advanced may have stopped using it long ago. Think about humanity's own trajectory. We have been broadcasting strong omnidirectional radio signals for roughly 100 years. But trends in communication technology are already moving away from high-powered, broadly dispersed transmission toward tightly focused encrypted digital communication. Powerful broadcast signals are giving way to fiber optics and direct link systems. As a civilization's communication infrastructure matures, it tends to become quieter and harder to detect from the outside. An advanced civilization might be effectively invisible to radio-based searches, not because it stopped communicating, but because it switched to communication methods we have not yet developed. Tightly focused laser pulses, neutrino-based signals, gravitational wave modulation. Any of these would pass through our current instruments without leaving a recognizable trace. What researchers are increasingly advocating for is a shift toward what they call technosignatures, evidence of technology that persists and scales beyond what individual broadcasts can offer. Heat signatures from industrialized planets, atmospheric chemistry that does not match any natural model, structured light curves from stars with engineered objects in orbit. These markers would be harder to hide and would not require a civilization to be actively trying to communicate. The logic is compelling. If you want to find a city, you do not listen for phone calls. You look for lights from above. Our current search strategy is the equivalent of listening for phone calls across an ocean. While the city we are looking for stopped using phones a century ago. The silence we hear may have nothing to do with absence. It may have everything to do with the limits of our instruments and the assumptions baked into our methods. This is an area of active, ongoing scientific debate. It is not a fringe argument. It is central to the current direction of astrobiology research and is increasingly influencing how funding bodies prioritize searches. And, speaking of things we may have already seen but not recognized, the next chapter concerns one of the most famous anomalies in the history of this entire search. A signal that appeared once, lasted 72 seconds, and has never been explained. If a civilization advanced enough to build structures visible from across the galaxy exists, it almost certainly would not announce itself with a radio broadcast. It would announce itself by reshaping its environment on a scale so enormous that the evidence would be embedded in the light of distant stars, detectable by any civilization patient enough to look. This is the logic behind the study of technosignatures. The search for physical evidence of technology rather than intentional communication. And the central object of that search is the Dyson sphere. Physicist Freeman Dyson proposed in 1960 that a civilization facing energy limitations would eventually recognize the most obvious available energy source, the full output of its star. A sufficiently advanced civilization would build a structure, not necessarily a solid shell, but perhaps a swarm of orbiting collectors and habitats that captures a significant fraction of its star's radiation. From the outside, a star surrounded by a Dyson swarm would appear anomalous. It would emit less visible light than expected for its mass and type, while radiating excess energy in the infrared spectrum. That specific signature, anomalously low visible output combined with anomalously high infrared emission, is something our instruments can detect across thousands of light years. Astronomers have cataloged candidates. None have been confirmed as artificial, but the search has only recently become systematic. The GIA mission, the Wide Field Infrared Survey Explorer, and upcoming missions like the Nancy Grace Roman Space Telescope are generating catalogues of stellar behavior at a scale that makes systematic signature searches possible. For the first time, researchers are using machine learning to flag stars that behave in ways inconsistent with known natural models, looking for irregular structured dimming patterns that an incomplete or partially constructed megastructure might produce. Beyond Dyson spheres, researchers are looking for other engineering signatures. Stars that appear to be losing mass in non-standard ways might be hosting mining operations on a planetary scale. Planetary systems with unusual orbital patterns might have been deliberately reorganized. Gas giants that have been stripped of their outer layers might bear the mark of resource extraction at a civilizational level. None of these have been confirmed, but the scientific community increasingly accepts techno-signature research as a legitimate, necessary component of any serious search for extraterrestrial intelligence. NASA formerly funded techno-signature research beginning in 2019, representing a significant institutional shift. One specific class of techno-signature has generated enormous scientific attention: starlight that dims in irregular non-periodic patterns. Not the clean repeating signals of a planet or binary star, but complex fluctuations that vary in depth, duration, and shape from one event to the next. This pattern is not what any known natural object consistently produces, and it has been detected in a real stellar system. The star responsible sits roughly 1,500 light-years away. Its behavior has generated more peer-reviewed papers, more competing hypotheses, and more genuine scientific controversy than almost any other single object in the last decade. What is happening around that star, and why scientists still cannot fully agree on a natural explanation after years of intensive observation, is the subject of the next chapter. And the longer you look at the data, the harder it is to feel settled. On August 15, 1977, a radio telescope at Ohio State University detected something unusual. The telescope was part of a program called Big Ear, one of the earliest organized searches for extraterrestrial radio signals. It scanned the sky automatically, printing the columns of data onto continuous paper. A volunteer named Jerry Emmon was reviewing the printouts days later when he noticed a sequence of numbers and letters that stood apart from everything surrounding it. The signal lasted exactly 72 seconds, the full duration that the telescope's field of view could hold any given point in the sky. It appeared to originate from the direction of the constellation Sagittarius. It had the intensity, the frequency, and the narrowband structure that researchers had theoretically predicted an artificial extraterrestrial signal might have. Eamon circled the data and wrote one word in the margin: "Wow." The signal has never been detected again. Dozens of follow-up observations have targeted the same region of sky using more powerful instruments over the past nearly 50 years. Nothing has returned. No repetition, no faint echo, no corroborating detection from any other telescope during the same window. Whatever produced it either appeared once, moved on, or stopped. This is confirmed observational data. The signal is real. Its characteristics are genuinely unusual. What produced it is entirely unknown. Over the decades, several natural explanations have been proposed. A comet releasing hydrogen gas in a specific direction was one of the more recent candidates proposed by astronomer Antonio Paris in 2017. His hypothesis generated significant attention and also significant skepticism. Multiple researchers examined his analysis and found that the comets he identified would not have been positioned correctly to produce the observed signal, and that the hydrogen gas explanation did not adequately account for the signal's narrowband character. The comet explanation is not accepted as definitive by the broader scientific community. The WOW signal sits in a rare and uncomfortable scientific category, an anomaly with no confirmed natural explanation, but also no confirmed artificial one. It is not proof of extraterrestrial intelligence. It is an unexplained data point, and science has to operate honestly within that distinction. What makes it particularly striking is the frequency. The signal appeared near 1,420 megahertz, the emission frequency of neutral hydrogen, the most common element in the universe. Decades before the detection, researchers had proposed that this frequency would be a logical choice for any civilization attempting contact, a universal radio landmark that any species studying the cosmos would recognize. The WOW signal appeared exactly there. Whether that is an extraordinary coincidence or something more meaningful, science cannot currently say. What it can say is that nearly 50 years of follow-up observation have not produced a satisfying natural explanation. That absence of explanation is not evidence of extraterrestrial origin, but it is evidence that we encountered something our models have not fully accounted for. One observation, one margin annotation. Nearly 50 years of silence from the same patch of sky. If the WOW signal was the most famous single anomaly of the last century. The next one arrived more recently, lasted years instead of seconds, and produced a level of scientific confusion the field had not seen in decades. In 2015, a paper published by astronomer Tabitha Boyajian and a team of collaborators described a star approximately 1,400 light-years away that was doing something no natural model could cleanly explain. The star, formerly catalogued as KIC 84628522, but almost universally known now as Tabby's star, was dimming, not in the regular periodic pattern produced by an orbiting planet, not in the smooth, predictable curve of a binary companion. It was dimming in complex, irregular bursts, sometimes by as much as 22% over a matter of days, then brightening, then dimming, again in a completely different pattern. 22% is an enormous dimming event for any star. A Jupiterized planet, one of the largest natural objects that could transit a star, blocks roughly 1% of stellar light. Whatever was blocking Tabby's star was by any natural measure impossibly large, and it was not regular, not symmetric, not consistent with any known type of orbiting body. The data came from the Kepler Space Telescope, which monitored over 150,000 stars simultaneously for planetary transits. In 4 years of observation, Tabby's star produced the most anomalous light curve in the entire data set. Citizen scientists involved in the Planet Hunters project flagged it as something they had never seen before. Their intuition was correct. Naturally, researchers initially explored the most dramatic explanation. The irregular dimming pattern is exactly what you might expect from a Dyson swarm. a collection of large orbiting structures at various stages of construction, blocking different amounts of light at different times as components move through the line of sight. This was not fringe speculation. It was raised in peer-reviewed publications and taken seriously by multiple researchers. The scientific community did not settle on that explanation. This is confirmed after years of intensive observation. The most widely accepted current hypothesis is that a cloud of disintegrating dust and debris, possibly the remnants of a shattered comet family or disrupted planetesimal belt, is responsible for the irregular dimming. But this explanation carries its own unresolved problems. The scale and structure of the dimming events remain difficult to fully account for with available natural models. More recently, astronomers detected that Tabby's star also shows a long-term gradual fading trend spanning years, a slow decrease in overall brightness that is entirely separate from the sharp transit events. This long-term behavior is also anomalous and adds another layer of complexity to any proposed explanation. Tabitha Boyagian herself has been careful and measured in her public statements, consistently emphasizing that the most likely explanation is natural, and that no evidence of artificial construction has been confirmed. That's scientific caution is appropriate. But she has also consistently acknowledged that the object has not been fully explained. What makes Tabby's star significant in the context of the Fermi Paradox is not any specific claim about its nature. It is what the object represents methodologically. For the first time, astronomers found a real stellar system exhibiting behavior that, without any bias toward dramatic conclusions, a techno-signature researcher would have flagged as a candidate worth serious investigation. The instruments worked. The anomaly was real. The natural explanation remained incomplete. That is not a discovery of alien technology. But it is a demonstration that searching for it this way might actually work. And if Tabby's star left researchers unsettled, the next anomaly did something far stranger. It did not sit in a distant system and dim. It traveled through our own solar system. It moved, and it refused to behave like anything we had ever catalogued. In 2007, astronomers reviewing archival data from the Parkes radio telescope in Australia found something that should not have been there. A burst of radio energy lasting only a few milliseconds, with an intensity so extreme it had to have originated from outside our galaxy. The burst was so short, so powerful, and so structurally unusual that the researchers spent years verifying it was not instrument error before publishing. It was not instrument error, and it was not alone. Since that first detection, astronomers have catalogued hundreds of fast radio bursts, brief flashes of radio energy lasting anywhere from a fraction of a millisecond to a few seconds, each one releasing more energy in that instant than our star emits over several days. They arrive from random directions across the sky, suggesting sources distributed throughout the universe rather than concentrated in any single region. Their exact physical origin was for years completely unknown. What deepened the mystery was repetition. Most fast radio bursts appeared once and never returned. Then, researchers discovered a small subset that repeated, sometimes irregularly, sometimes in structured cycles. One source cataloged as FRB 121102 has been observed to repeat in bursts that cluster periodically, then go quiet, then cluster again. The period of that cycle is approximately 157 days, regular enough to suggest a mechanism, irregular enough to resist simple explanation. The leading scientific explanation today points to magnetars, highly magnetized neutron stars that are among the most extreme physical environments in the known universe. A magnetar can release enormous amounts of electromagnetic energy during starquake events, when the stresses on its rigid crust cause sudden fractures. In 2020, astronomers detected a fast radio burst from a magnetar within our own galaxy. The first time such an event was confirmed to have a known source. This was a significant scientific milestone. It demonstrated that magnetars can produce at least some fast radio bursts. But it did not close every open question. The energy levels of some observed bursts, particularly those from distant galaxies, exceed what current magnetar models predict under standard physics. The structured periodicity of repeating sources remains incompletely explained, and the sheer variety in burst characteristics, shapes, durations, frequencies, and repetition patterns suggests that a single source type may not account for everything in the catalog. Some researchers have explored whether a subset of fast radio bursts could represent technosignatures. The energy required to produce a burst at the levels we detect from extragalactic distances is so enormous that, if it were artificial, the engineering involved would be on a scale that dwarfs anything imaginable today. Physicist Avi Low of Harvard has proposed that a powerful enough artificial emitter designed for interstellar propulsion rather than communication could theoretically produce a fast radio burst as a byproduct. He calls this the lighthouse model. This is not the scientific consensus. It is a theoretical possibility raised by a credentialed researcher and not yet ruled out. What fast radio bursts do confirm regardless of their origin is that the universe contains physical processes producing structured energetic emissions on timescales and at intensities that we are only beginning to characterize. Every time we have opened a new observational window on the cosmos, we have found things we did not expect. Fast radio bursts were invisible to us until 2 decades ago. What else is currently invisible? But compared to what entered our solar system in 2017, fast radio bursts feel safely distant. What came next did not stay at a polite extragalactic remove. It came to us on October 19, 2017. An astronomer at the Haleakala Observatory in Hawaii detected a fast-moving object passing through our solar system. Initial calculations suggested it was a comet from within our own neighborhood. Closer analysis revealed something that stopped the field cold. The object had come from outside the solar system entirely. It was the first confirmed interstellar visitor ever detected. They named it Oumuamua, a Hawaiian word meaning roughly a messenger from afar arriving first. At first, astronomers expected a straightforward classification. An interstellar rock or icy body ejected from some distant stellar system and drifting through space for millions of years before a chance gravitational encounter brought it through ours. The universe is old. Ejected debris should be everywhere. Finding one passing through was surprising, but scientifically manageable. Then the data came back, and manageable became the wrong word. Oumuamua was shaped unlike any natural object previously cataloged. Estimates based on its reflectivity and brightness variation suggested it was extremely elongated with a length-to-width ratio of perhaps 10:1 or more. No known natural formation process reliably produces objects with that geometry at that scale. Comets are irregular, but not blade-like. Asteroids vary, but not that dramatically. The shape alone was anomalous. Then came the trajectory problem, as Oumuamua moved away from our star. It accelerated not dramatically, but measurably and persistently beyond what gravity alone could account for. Comets accelerate this way when heat from a nearby star vaporizes subsurface ices, creating outgassing jets that push the object. This is well understood. Astronomers looked for signs of outgassing. They found none. No detectable gas cloud, no dust trail, no coma, just clean, unexplained acceleration. Every proposed natural explanation for the anomalous acceleration has been published and challenged. One hypothesis suggested it was made of hydrogen ice, which would outgas invisibly. The problem: hydrogen ice is not stable in the interstellar environment long enough to survive the journey implied by its trajectory. Another suggested it was a thin, flat piece of natural material pushed by radiation pressure from our star like a natural solar sail. The problem? An object thin enough to be pushed that way by light would have to be no more than a millimeter thick across a surface hundreds of meters wide. A geometry with no known natural formation mechanism. Avi Loeb of Harvard, one of the most prominent astrophysicists in the field, argued publicly and in a published book that the most parsimonious explanation for Oumuamua's properties taken together was that it was artificial, not that it was certainly artificial, that, given the anomalies, the hypothesis deserved serious scientific consideration rather than reflexive dismissal. The mainstream scientific community disagreed, largely maintaining that a natural explanation would eventually emerge. In 2023, researchers proposed a new mechanism involving nitrogen ice fragments from a shattered exoplanet surface, which could theoretically produce the observed characteristics. This explanation received attention, but has not achieved universal acceptance. What Oumuamua confirmed regardless of its origin is that interstellar objects pass through our solar system, and that at least one of them behaved in ways our models did not predict. A second interstellar object, Borisov, arrived in 2019 and behaved perfectly normally, exactly like a comet. The contrast only deepened the strangeness of the first. The full story of Oumuamua is not closed. The object is long gone, too distant now for any instrument to reach or observe. Whatever it was, it passed through and left us with questions we still cannot answer. And if something from outside our solar system could arrive without warning and leave without explanation, it forces a harder question. What else might be out there that we are not equipped to recognize? One of the quieter explanations for the Fermi Paradox does not require aliens to be rare, destroyed, or hiding. It requires only that the universe is structured in a way that makes traveling across it fundamentally physically prohibitive for any civilization, regardless of how advanced. And the more carefully you examine the physics, the harder it is to dismiss. The first barrier is energy. To accelerate a spacecraft to even 1/10 of light speed, the minimum velocity considered relevant for practical interstellar travel within a human lifetime, requires an energy expenditure that dwarfs anything our civilization currently produces. For a vehicle with the mass of a modest spacecraft, the energy required approaches what would be generated by thousands of nuclear detonations just to reach that fraction of light speed. Scale the vehicle up. Add life support systems, fuel, reserves, and shielding, and the energy requirements become staggering. Then there is the fuel paradox. Any rocket-based system has to carry its own fuel, but fuel has mass. More mass requires more fuel to accelerate it. The relationship is exponential, not linear. As mission distances increase, the required fuel mass rapidly reaches absurd proportions. Chemical rockets are obviously inadequate. Nuclear propulsion improves the situation but does not solve it. Fusion drives, if achieved, would help significantly. But even under optimistic fusion scenarios, the engineering required for a crewed interstellar mission represents centuries of advancement beyond our current capability. The second barrier is time. Even at 1/10 of light speed, the journey to the nearest confirmed stellar system, Proxima Centauri, takes approximately 40 years. The nearest star systems that might host Earth-like planets are further. For a civilization attempting to survey a galaxy 200,000 light-years across, the timescales involved are almost impossible to internalize. Even sending probes at significant fractions of light speed across the full breadth of the galaxy would take millions of years. Civilizations waiting for their probes to return or their colonies to report back would need institutional stability across timescales that exceed the entire recorded history of human civilization, thousands of times over. The third barrier is collision risk. At high velocities, interstellar space is not empty. Dust grains and small particles, invisible and essentially undetectable at interstellar distances, become lethal at relativistic speeds. A particle no larger than a grain of sand, encountered at a significant fraction of light speed, carries the kinetic energy of a small explosive. Shielding against such collisions across decades-long journeys is an engineering problem with no current solution. These barriers are real. They are confirmed by physics. They do not disappear with optimism or clever narrative framing. What they suggest for the Fermi Paradox is that even civilizations far in advance of us may have concluded that physical interstellar travel is not viable as a general strategy. The galaxy may be populated with intelligent species that have never left their home systems. Not because they lack the will or curiosity, but because the physics simply does not cooperate. In that scenario, the silence is not a sign of absence, it is a sign of confinement. Each civilization locked in its own small sphere of space, perhaps listening, perhaps transmitting, but unable to bridge the distances that separate them. If that confinement is real and universal, the next question becomes even stranger. Could a civilization still leave a detectable mark without physically traveling? And do any marks already exist that we have not yet learned to read? Most discussions of the Fermi Paradox treat the problem as a spatial one. Where are they? Why have they not come here? But there is an equally powerful version of the same problem that operates entirely in time. And it may be more unsettling than any of the spatial arguments. The universe is 13.8 billion years old. Complex life on Earth took roughly 4 billion years to produce intelligence. If the emergence of intelligence is even somewhat probable given the right conditions, and if those conditions existed elsewhere in the galaxy, several billion years before they existed on Earth, then there may be civilizations whose entire rise development and possible extinction occurred billions of years before a single human ancestor walked upright. A civilization that peaked 2 billion years ago would leave no radio signals detectable today. Its broadcasts, if they ever reached our region of space, would have passed through billions of years ago, when the only life on Earth was single-celled organisms with no instruments and no awareness. Any physical artifacts they launched into space would be indistinguishable by now from natural debris, weathered and redistributed by billions of years of cosmic processes. The inverse is also true. Civilizations that will emerge in the future, millions or billions of years from now, when stellar conditions have evolved further, will arrive long after we are gone. From their perspective, we will be the ancient and silent ones. Our transmissions will have faded. Our artifacts, if any, survive, will be incomprehensible relics. This is sometimes called the temporal communication problem. Two civilizations can occupy the same galaxy and yet be so separated in time that they never have the opportunity to even sense each other's existence. The overlap required for detection is not just proximity in space. It is proximity in time and on cosmic scales that is a far narrower window. Astronomer Milan Kirovich has written extensively on this idea, arguing that our search for extraterrestrial intelligence is built on an implicit assumption that civilizations exist on timescales similar to ours. If civilizations can last millions or billions of years, the galaxy's history of intelligence might be mostly in its past, not its present. We might be searching for something that flourished and faded long before our instruments existed. There is also a forward-looking version of this argument that contains its own disturbing implication. If intelligence is genuinely rare, and we are among the first, then the full flowering of minds in this universe may lie tens or hundreds of millions of years in the future. We are not late arrivals to an empty party. We are the very early ones, and the party itself has barely started. Whether that framing is hopeful or isolating probably depends on the day you are having. What it does is shift the question from where is everybody to when is everybody, and in doing so, it removes the urgency from the silence. The galaxy may not be empty. It may simply be early, but there is a different class of civilizations that might exist right now, in this moment that no telescope can find. Not because they are hiding, not because they are destroyed, but because they never developed any technology we would recognize as a signal at all. There is an assumption so deeply embedded in the search for extraterrestrial intelligence that it almost never gets examined directly. The assumption is that intelligence leads to technology, that any species capable of abstract reasoning will eventually build machines, generate electromagnetic signals, and leave a detectable mark on its environment. Earth's history supports this, but Earth's history is a sample size of one. Consider the cognitive sophistication of some Earth species that never developed technology. Dolphins have demonstrated self-recognition, complex social structures, regional dialects, and problem-solving abilities that would have seemed extraordinary to earlier generations of researchers. Elephants grieve their dead, maintain multi-generational social memory, and cooperate in ways that suggest genuine strategic awareness. Crows and ravens manufacture tools, plan for future scenarios, and recognize individual human faces, distinguishing friends from threats across years. Octopuses display problem-solving and learning behaviors that evolved completely independently from vertebrate intelligence, suggesting that cognitive sophistication can arise through radically different biological pathways. None of these species are building radio transmitters. Intelligence and technological civilization are not the same thing. Intelligence is a cognitive trait. Technological civilization is a specific cultural and biological trajectory that depends on a cluster of factors that may not be universal. Hands capable of fine manipulation. Social structures that enable large-scale cooperation and knowledge transmission. Sufficient environmental pressure to drive innovation rather than stability. A metabolism and lifespan that rewards long-term investment in tools. Remove any of these from the equation, and you can have a planet full of intelligent beings who live rich, complex cognitive lives while leaving essentially no trace detectable from space. An ocean world, for example, could sustain enormous populations of intelligent marine organisms with no access to fire, no ability to smelt metal, and no path to electronics. Their intelligence might be profound. Their civilization, by any internal measure, might be sophisticated and ancient. From space, their planet would look like a featureless water world. This possibility scales uncomfortably well. If even a significant fraction of planets with intelligent life host species that never develop detectable technology, the silence is explained without any filter, any catastrophe, or any hiding. The universe is full of minds we simply cannot see, because we are only looking for the specific technological signatures that our own path produced. Some astrobiologists have begun taking this seriously enough to propose that the definition of intelligence used in the search for extraterrestrial intelligence is too narrow. We are not searching for intelligence. We are searching for industrial civilization, and there is no guarantee that intelligence and industry travel together across all possible biospheres. This does not resolve the deeper question. Even one civilization that developed technology in 4 billion years of Earth history managed to do it. Statistically, that seems like it should happen elsewhere. But the argument from non-technological intelligence adds another layer to the silence. Some of what we are not hearing may not be silence at all. It may be a conversation in a language we have not imagined. And the next layer of that idea goes deeper still. Because even among species that do develop technology, the very structure of their minds might make it impossible for us to recognize what they are building or saying. In the last decade, the catalog of potentially habitable worlds in our solar system has expanded dramatically. Not through discoveries of Earth-like rocky planets with thin atmospheres and open skies, but through something entirely different. Worlds with liquid water, hidden beneath thick outer shells of ice, insulated from the cold of space by the pressure of kilometres of frozen crust. These ocean worlds are now considered among the most promising candidates for life in our solar system, and possibly in the universe. Europa, one of Jupiter's moons, is estimated to contain twice the volume of liquid water present across all of Earth's oceans. It sits beneath an ice shell potentially dozens of kilometres thick, kept warm not by sunlight, but by tidal flexing generated by Jupiter's enormous gravitational pull. The seafloor may host hydrothermal vents similar to those on Earth, where chemical energy rather than light drives ecosystems in total darkness. Life exists around Earth's hydrothermal vents completely independently of sunlight. This is confirmed. Enceladus, a moon of Saturn, actively ejects plumes of water vapor and ice particles from its south polar region. Analysis by the Cassini spacecraft detected molecular hydrogen, silica, and organic compounds in those plumes, the chemical signatures of hydrothermal activity, and the building blocks of biology. Enceladus is actively venting material from its subsurface ocean into space. Whatever is in that ocean is in a sense already reaching us. Titan, also orbiting Saturn, has a different kind of liquid environment. Dense hydrocarbon lakes on its surface suggest the possibility of chemistry-based life operating on entirely different principles than water-based biology. Titan's atmosphere is thicker than Earth's and rich in organic compounds. Researchers have proposed theoretical metabolisms that could operate in liquid methane rather than water. Now consider the Fermi implications. A civilization that evolved in a sealed subsurface ocean beneath kilometres of ice faces an almost insurmountable barrier. to any kind of space-based communication or exploration. They would have no access to the electromagnetic sky above them, no stars, no radio frequencies, no line of sight to anything beyond their world. Their entire observable universe would be the ocean around them and the rock beneath them. Even if such a civilization developed intelligence, language, culture, and sophisticated technology adapted to their environment, the path to radio transmission or space exploration would require them to first understand that a universe existed above their ice ceiling, then penetrate kilometers of solid ice, then survive in a vacuum for which nothing in their biology or experience had prepared them. The obstacles are not merely engineering problems, they are conceptual ones. A civilization that has never seen a star does not naturally arrive at the idea of broadcasting into space. Thousands of ocean worlds may exist across the galaxy right now, some of them harboring complex life, perhaps intelligent life, locked in silence beneath their shells. Not silent by choice, silent by architecture. This matters enormously for how we think about the Fermi Paradox. If a significant fraction of habitable environments in the universe are enclosed rather than open, the pool of civilizations capable of electromagnetic communication is far smaller than the pool of civilizations that exist. We are not just searching for life. We are searching for a specific subset of life that happened to evolve in an environment compatible with the particular kind of curiosity that builds telescopes. But even among civilizations that do have access to open skies and vast electromagnetic possibility, there may be a barrier just as impenetrable as a kilometer of ice. A barrier made not of rock or vacuum, but of thought itself. When we search for extraterrestrial intelligence, we are searching for something that looks enough like our own intelligence that we can identify it. Structured mathematical, sequences, consistent frequency patterns, artifacts with geometric precision. The implicit assumption is that intelligence produces recognizable order. But that assumption has never been tested against anything other than human intelligence. Our concept of what constitutes a signal is built entirely on what our own minds produce. We look for prime number sequences because we would broadcast prime numbers. We flag anomalous geometric structures because we build geometric structures. The entire search methodology is at its foundation a projection of human cognitive style onto a universe we have never actually sampled for cognitive diversity. Consider what an entirely alien intelligence might look like. Not an intelligence that shares our evolutionary pressures, our sensory inputs, our social structures, or our relationship with time. Something that developed under fundamentally different constraints on a fundamentally different world. Perhaps with multiple simultaneous processing streams rather than a single linear thread of consciousness. Perhaps with a relationship to information storage and retrieval that operates across a biological substrate. Nothing like our nervous system. There is no guarantee such an intelligence would produce anything we recognize as structured communication. Its artifacts might look to our instruments like natural noise. Its signals might carry information in dimensions we do not monitor. Its technology might operate on physical principles we understand theoretically but have not yet observed being applied. We would look directly at the evidence and see nothing, not because nothing is there, but because we lack the cognitive or instrumental framework to pass it. Researchers studying animal cognition have encountered small versions of this problem on Earth. For decades, animal communication systems were evaluated by whether they resembled human language. Species that did not pass that test were classified as non-linguistic. as researchers developed new frameworks for analyzing non-human communication. Previously invisible complexity emerged. Prairie dog calls have been shown to encode surprisingly specific information about predator characteristics. Whale song contains structural features that share certain mathematical properties with human language. Bee dances communicate distance and direction through a physical medium that no human sensory system can directly read. These are animals that share billions of years of evolutionary history with us. An alien intelligence sharing none of that history might be so fundamentally different in its cognitive architecture that the gap is not a matter of translation, but of category. The tools we build to listen are tuned to patterns our minds can process. Patterns our minds cannot process will pass through those tools invisibly. This is a genuinely sobering scientific point. The Fermi Paradox may not be asking the right question. The question is not, where is everybody? It may be whether we could identify everybody, even if they were in some sense present. The silence might be a communication breakdown at the deepest possible level, not a failure to transmit, a failure to perceive. And if that cognitive barrier applies to what we can receive, it applies equally to what we can send. Any message we broadcast is built to the specifications of a human mind. Whether it means anything to a radically different kind of intelligence is a question we cannot answer from the inside. This leads to one of the most unsettling ideas on this list. Not that intelligence is out there in hiding, not that it rose and fell, but that it might have arrived here long ago and left something behind. Something we have been looking at for billions of years without realizing what it is. In 1973, molecular biologist Francis Crick, who shared the Nobel Prize for co-discovering the structure of DNA, published a scientific paper with astronomer Leslie Orrell proposing something that the scientific establishment received with considerable skepticism. Their hypothesis, which they called directed panspermia, suggested that life on Earth did not originate here through purely natural chemistry. It was deliberately seeded by an extraterrestrial civilization. Crick arrived at this idea not through mysticism, but through biochemistry. He was troubled by what he saw as the extreme improbability of the spontaneous generation of life from raw chemistry within the time window available on early Earth. Life appeared remarkably quickly after Earth's surface cooled. The genetic code is also extraordinarily universal, a single code shared by every known form of life on Earth, from bacteria to redwood trees to humans. Crick found this universality suspicious. It suggested either one common origin or deliberate design with a standardized system. Directed panspermia proposes that a sufficiently advanced civilization facing the eventual death of its star or other existential pressures might have seeded numerous worlds across the galaxy with microbial life or the chemical precursors to life. Not to colonize, not to communicate, simply to propagate biology as widely as possible, ensuring that wherever conditions eventually became favorable, the process of life would begin. If this hypothesis is correct, it reframes the Fermi paradox significantly. The origin of life on Earth might not be an independent data point at all. It might be evidence of a prior civilization that no longer exists, or that exists in a form we do not recognize. The silence we observe would be the silence of an ancestor, a civilization that may have peaked billions of years ago, seeded what it could, and then faded. The hypothesis is by its nature almost impossible to confirm or refute. The genetic code's universality can be explained by common descent from a single origin point without invoking extraterrestrial agents. The speed of life's appearance on early Earth, while surprising, has proposed natural explanations that Crick's critics considered adequate. What the hypothesis does productively is force a different kind of question about the search for life. If panspermia directed or natural is a real mechanism, then finding life elsewhere in the galaxy would not necessarily indicate an independent origin. Two worlds with life might share a common biological ancestry, either through natural transport of material between star systems during early solar system formation events, or through deliberate seeding by a civilization we have no other evidence for. A recent area of research supports at least the natural version of this idea. Rocks ejected from planetary systems during formation can travel between stars over millions of years, occasionally landing on new worlds. If those rocks carry dormant microbial life, as some research suggests is physically possible, then life could propagate across star systems without any civilization's involvement. The directed version simply adds intent to a mechanism that may operate naturally. Whether or not any civilization deliberately seeded the galaxy with life, the question of our own origins may be less settled than biology textbooks suggest. The precise mechanism by which chemistry became biology on Earth remains as of today an open scientific question. Crick's hypothesis sits at the edge of that opening, and if we were placed here intentionally, the civilization that placed us here may have left more than just life. Some researchers have begun asking whether the answer to the Fermi Paradox might not require any telescope at all. It might require looking somewhere much closer. In 2001, philosopher Stephen Webb formulated a hypothesis that occupies a strange position between the simulation argument and something more specific, and in some ways more disturbing. He called it the planetarium hypothesis. The idea is not that we live in a fully simulated universe. It is that the cosmos visible to us has been deliberately constructed to appear empty, a kind of cosmic theater designed to isolate us from the reality of what the universe actually contains. The premise begins with a straightforward observation. Every piece of information we have about the universe beyond our solar system comes from electromagnetic radiation, light, radio waves, X-rays, gravitational waves. Every distant star, galaxy, and cosmic structure we have mapped is known to us only through signals that have traveled to our instruments. We have never directly visited anything beyond our own immediate cosmic neighborhood. Our entire picture of the universe is built from what reaches us here. This creates a vulnerability. A sufficiently advanced civilization that wished to construct a false picture of an empty universe would not need to alter the actual universe. It would need only to manage the signals reaching our solar system. If such a civilization could intercept or overlay the electromagnetic information arriving at Earth, replacing the signatures of inhabited worlds and alien megastructures with empty static or natural-look noise, we would have no way of knowing. The planetarium hypothesis is in one reading a sophisticated extension of the zoo hypothesis. Under the zoo model, civilizations simply stay quiet. Under the planetarium model, they actively maintain the illusion of emptiness, managing what we see so completely that our most powerful telescopes find nothing because they have been designed from the outside to find nothing. This hypothesis is not testable with any current instrument. That is its most significant scientific weakness. An illusion designed by a sufficiently advanced civilization to be undetectable would by definition be undetectable to us. Every observation we make could be within the managed zone. Every anomaly we dismiss as natural could be a seam in the construction. This makes the planetarium hypothesis less a scientific proposition than a boundary condition on scientific epistemology. It marks the edge of what we can know from inside the system we are trying to analyze. If the inputs to our analysis are controlled, our outputs are meaningless. This is a genuinely uncomfortable position for science to sit in. What the hypothesis shares with other advanced civilization solutions to Fermi is the implication that the silence is intentional, not a product of rarity or destruction or distance, a product of management. The universe looks empty because something wants it to look empty. Whether that something is benevolent, curious, cautious, or indifferent to our perception of reality is a question the hypothesis provides no framework for answering. There's a different version of this idea that does not require active deception. It requires only that the observable universe, the portion accessible to our instruments given the speed of light and the age of the cosmos, is simply too small a sample to contain evidence of intelligence that exists beyond it. The universe may be vastly larger than what we can observe. Other civilizations may exist at distances so extreme that their light has not had time to reach us since they formed. The silence of our observable bubble is not the silence of the universe. It is the silence of our corner of it. Either way, we are working with incomplete information. And the most haunting question may be whether the incompleteness is accidental or arranged. What comes next is not philosophy. It is biology, and it may contain the most personal version of the Fermi answer yet. For decades, the search for life beyond Earth operated almost entirely in the realm of theory. Researchers built models, ran simulations, and debated probabilities. While the actual observational data remained frustratingly sparse, that situation has begun to change, and the shift is significant enough that some researchers describe the current decade as the beginning of a genuinely new era in astrobiology. The James Webb Space Telescope, launched in late 2021 and fully operational by 2022, has given astronomers the ability to analyze the atmospheric composition of exoplanets with a precision that was previously impossible. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere before reaching our instruments. Different molecules absorb different wavelengths of light in characteristic patterns. By analyzing which wavelengths are missing from that filtered light, researchers can identify atmospheric compounds from thousands of light years away. In 2023, researchers using James Webb announced the detection of carbon dioxide and sulfur dioxide in the atmosphere of a planet called K28b. A world approximately 2.5 times the size of Earth orbiting in the habitable zone of a cool star about 120 light-years away. Sulfur dioxide can be produced by photochemical reactions involving biological molecules in ocean water under certain conditions. This finding was described by the research team as tentative and in need of follow-up confirmation. It was not claimed as proof of life. Then, in 2025, the same research team published results announcing the detection of what appeared to be dimethyl sulfide in the same planet's atmosphere. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. It has no confirmed abiotic production pathway at the concentrations the data suggested. The signal was described as more than 3 sigma in statistical significance, meaning strong enough to be taken seriously, but not yet at the 5 sigma threshold typically required for a confirmed discovery in physics and astronomy. The scientific community responded with both excitement and appropriate caution. Several independent researchers raised concerns about the statistical interpretation of the data and the challenges of distinguishing weak signals from instrument noise at these distances. The detection has not been refuted. It has not been confirmed. It is currently the subject of ongoing analysis and debate, exactly as the scientific process requires. What this represents, regardless of the final verdict on K218b, is a proof of concept. The instruments now exist to detect biologically relevant atmospheric chemistry on distant worlds. Within this decade, with continued James Webb observations and the eventual deployment of next-generation telescopes currently in development, researchers expect to have analyzed the atmospheres of dozens of habitable zone planets with sufficient precision to begin building a statistical picture. If multiple independent worlds show atmospheric signatures inconsistent with purely abiotic chemistry, the case for widespread life becomes difficult to argue against. If every habitable world we examine shows only chemical equilibrium and no biological perturbation, the case for the rare Earth hypothesis or the great filter strengthens considerably. The answer to the Fermi Paradox may, for the first time in history, be within the reach of instruments we have already built. But if we do find evidence of life elsewhere, a different and very human problem immediately arises, one that researchers are already debating with unusual intensity. The search for extraterrestrial intelligence is, by its historical design, passive. We listen, we scan, we catalog anomalies. We have not, as a civilization, made any systematic decision to actively and powerfully broadcast our presence to the cosmos. That is beginning to change, and the scientific community is deeply divided about whether that change is wise. METI stands for Messaging Extraterrestrial Intelligence. Unlike passive listening programs, METI involves deliberately transmitting powerful targeted signals towards specific stellar systems in the hope of making contact. The logic is straightforward. If every civilization waits for someone else to transmit first, nobody ever makes contact. Someone has to go first. The counter-argument is equally direct. We do not know who is listening. We do not know their intentions. We do not know their power relative to ours. Announcing our location and capability level to an unknown audience carries risks that cannot be quantified, and risks that cannot be quantified cannot be managed. Stephen Hawking publicly stated before his death that attempting to contact extraterrestrial civilizations was, in his assessment, dangerous. He argued by analogy to historical contact between technologically unequal civilizations on Earth, where the outcome for the less advanced was consistently catastrophic. He was not alone. A significant number of researchers in astrobiology, astrophysics, and existential risk have argued that active messaging should require global consensus before proceeding. Given that any response to a transmitted signal would arrive after a delay of decades to centuries and would affect all of humanity, not just those who sent the message, others argue the opposite. If the dark forest scenario is real, we are already detectable. 100 years of broadcast radio and television signals have created an expanding bubble of electromagnetic activity that is already more than 100 light-years in radius. Any civilization within that range already knows we exist. Silence now does not undo that. If we are already visible, the argument for remaining quiet has limited practical force. The debate also touches on governance questions that science alone cannot resolve. Who has the authority to speak for Earth? No international treaty currently governs METI. Individual observatories and private organizations can, in principle, transmit whatever they choose. Several powerful targeted transmissions have already been sent without any global consultation, including a high-powered broadcast toward a star system in 2008. What makes the METI debate more than academic is timing. The development of high-powered phased array transmitters and advances in targeting precision now make it technically feasible to send signals powerful enough to be detected at stellar distances. The capability exists. The will exists in at least some quarters. What does not exist is consensus, protocol, or governance. The question of whether to shout into the dark, knowing nothing about what might shout back, or fall silent and wait in a universe that may already have heard us, is one of the first genuinely civilizational scale decisions humanity faces in the domain of space. And it may be the most consequential one we make this century, with effects that neither we nor our grandchildren will live to see fully resolved. But the most unsettling suggestion about the Fermi Paradox may not involve anything we send outward. It may involve something that has been with us since the very beginning. There is a version of the Fermi answer that requires no telescope, no signal, and no distant world. It requires only a careful look at ourselves, at our DNA, our biochemistry, and the specific molecular record written into every cell of every organism on Earth. The idea begins with a genuine scientific puzzle. The genetic code is universal. Every known form of life on Earth, every bacterium, every plant, every animal, uses the same basic coding system to translate DNA into proteins. The code maps specific triplets of chemical letters onto specific amino acids, and this mapping is essentially identical across all life. This universality is explained by common ancestry. All life descending from a single original population, which is the scientific consensus. But some researchers have asked a harder question. Why this particular code? Of the enormous number of possible mappings between triplets and amino acids. The specific code used by all life on Earth appears to be highly optimized. Studies have shown that it is extraordinarily resistant to mutation errors. That single errors in the code produce minimal changes in protein function compared to most random, alternative codes. The probability of arriving at a code this optimized through purely random initial assignment is, by some mathematical analyses, extremely small. This could mean the code was selected through early evolutionary pressure on early Earth, before the last universal common ancestor in a period we have almost no direct fossil record of. That is the standard scientific position. It could also, in a more speculative framing, mean the code was designed. Physicist Paul Davies has written about what he describes as the possibility of a cosmic legacy. The idea that a sufficiently advanced civilization might encode information into the genome of a biological organism seeded across the galaxy, not as communication in any conventional sense, but as an archive. DNA is extraordinarily information-dense and extraordinarily stable under the right conditions. A message encoded in non-coding regions of DNA, the roughly 98% of the human genome that does not directly code for proteins, could, theoretically, persist for billions of years. This idea has moved from pure speculation into, at minimum, scientific curiosity. Researchers have begun systematically analyzing genomic data for mathematical structures or information patterns inconsistent with purely evolutionary origin. No confirmed result has emerged, but the methodology is new, and the analysis is ongoing. There is also a simpler biological version of this idea that does not require encoded messages. If life on Earth was seeded from another world, whether intentionally or through natural interstellar transport, then our biology itself is evidence of life's presence elsewhere. Every cell in your body may carry the chemical signature of an origin that began somewhere other than Earth, not metaphorically, physically. Whether our biology is a record of our own planet's chemistry, or a letter from somewhere further away, the answer to the Fermi Paradox may have been inside us all along. Not in our technology, not in our telescopes, in the molecule that defines every living thing we have ever found. We have been searching the sky for signals. The deepest signal may be the one we are built from. Every theory we have explored offers a different answer. Some suggest the universe is full of life too simple to signal. Some suggest civilizations rise and destroy themselves before reaching out. Some suggest intelligence is so rare that we may be the only minds that have ever formed in this corner of reality. Some suggest the silence is managed or temporal, or a product of our own limited perception. We do not know which is true. That uncertainty is not a failure of science. It is the honest frontier of what any civilization can know at our current stage. But suppose we sit with the most austere possibility that the silence is real, that it is permanent, that there are no other technological civilizations in this galaxy, that none have sent probes or signals or artifacts that we can detect, and that the reason is some combination of everything we have examined. Life is rare. Complexity is rarer. Intelligence is rarer still. And the civilizations that do emerge tend to be brief, separated by unbridgeable distances in space and time. If that is true, what does it mean? First, it transforms our sense of responsibility. If we are the only minds in this galaxy capable of asking these questions, of looking at the cosmos and understanding what it is, then our survival is not merely a human concern. It becomes a cosmic one. The universe has in us produced something that can observe it, understand it, and perhaps eventually shape parts of it. If we destroy ourselves, that capacity goes with us. There is no backup, no second chance from a neighboring civilization that might carry the torch. Second, it changes the meaning of what we build. Every piece of knowledge we accumulate, every scientific advance, every cultural achievement exists in a context where it may be the only such thing in the galaxy. Not the best version of a common thing, the only version of a rare one. That does not make our problems smaller, or our conflicts less real, but it adds a dimension to their stakes that the Fermi Paradox makes impossible to ignore. Third, it reframes exploration. If the galaxy is largely empty, the long and difficult project of becoming an interstellar civilization is not the act of joining a populated cosmos. It is the act of filling an empty one. Every world we eventually reach, every system we study and potentially inhabit, we would arrive at as the first mind ever to encounter it. The strangeness and weight of that firstness is difficult to hold in the mind all at once. Fourth, and perhaps most importantly for the present moment, it gives urgent meaning to the question of whether we survive our own critical phase. The century we are living through is widely recognized by researchers in existential risk as one of the most consequential in our species' history. Artificial intelligence, biotechnology, climate disruption, and the geopolitical pressures that accompany rapid technological change are all converging in a window that is, by the standards of cosmic time, almost instantaneously brief. Whether we navigate it matters enormously if we are alone. It matters even more if our survival might one day answer the question for another species millions of years from now, that looks at the sky and wonders whether they are the only ones. We began this journey with a simple question: where is everybody? We have moved through 30 layers of possible answers, and arrived not at a single clean solution, but at a portrait of a universe that is in every direction asking something back. Whether life is common or rare, whether the filter is behind us or ahead, whether the silence is natural or managed, the silence itself carries a message. It tells us that whatever we are, it is not ordinary, and whatever happens next, we are the ones who decide it. The universe is watching or it is not.